Swayam Prabha. Digital India. Educated India.
We are going to discuss the working principle of another very popular fuzzy reasoning tool, that is known as Takagi and Sugeno's approach. Now, here in Takagi and Sugeno's approach, what I do is a particular rule, say ith rule, is represented as follows. Now, here the rule is written like this: if x 1 is a 1 I and x 2 is a 2 I, and there are a few terms here, and x n is a n I, then y I is nothing but a naught I plus a 1 I x 1 plus there are a few terms, and the last term is a n I x n. Now, here I have already mentioned little bit that in this approach, so a particular rule, the output of a rule, so that is nothing but the function of the input parameters or the input variables. Now, here in this rule I am considering that there are n such variables like your x 1, x 2 up to x n. So, this output, that is y I, that is represented as a function of the input parameters. Now, if you see, we have got a few coefficients, for example, say a naught I, then comes a 1 I, a n I, these are all coefficients. Now, these coefficients are to be predetermined. How to determine that? Now, what we do is we take the help of some optimization tool and with the help of some available data. So, we try to find out what should be the numerical values of these particular the coefficients. Now, generally we use an optimization tool that is known as least square technique. So, this least square technique actually we generally use to find out the values for the coefficients. Now, you can see this output as a linear function of the input parameters, and that is why. So, this approach can be termed as nonlinear. For a nonlinear system, we try to approximate by a number of linear system. So, this is nothing but actually the nonlinear systems representation as a combination of several linear system. Now, here if I know the ith rule, now what we do is we try to find out the strength of the ith rule or the weight of the ith rule. Now, this weight of the ith rule is represented as mu a 1 I x 1 multiplied by actually mu a 2 I x 2, and here there are a few terms, and the last term is actually mu a n I x n. That means, the strength of the ith rule, that is represented as the membership value of a 1 corresponding to the ith rule the moment I am passing this x 1 as the input variable, multiplied by the mu a 2 the corresponding to the ith rule, and the moment I am passing this x 2 as the input variable. So, all such mu values we try to find out, and the last term is nothing but a n I corresponding to your x n. So, here as if we are passing all the input parameters or the input variables like x 1, x 2 and x n, and we try to find out what should be the mu value, what should be the mu value and what should be the mu value, and after that we multiply all the mu values, and that will be the weight of the ith rule. And once you have got this particular weight of the ith rule, now next what we can do is we can find out the output very easily using this particular the expression. Now, for the combined control action, this output y is nothing but summation I equals to 1 to k w I multiplied by y I divided by your summation I equals to 1 to k w I. Now, here k indicates the number of the fired rules, and what is y I? Y I is nothing but the output corresponding to your the ith rule, and this w I is nothing but the weight. Now, how to determine? So, this particular the output which is a function of the input parameters. So, that I am going to discuss after some time, but before that let me tell you that here in Takagi and Sugeno's approach, the way we express the output as a function of the input parameters. Now, if I just read one rule, so no control action will be coming to my mind, and that is why actually here the interpretability is much less, although we can go for a better accuracy, because we take the help of some optimizer, some optimization tool, and if you just optimize with the help of some known data. So, there is a possibility you will be getting very accurate coefficients, the values of the coefficients, and ultimately you will be getting very accurate output. So, the prediction will be really good and very accurate in this Takagi and Sugeno's approach. Now, to explain the working principle of this approach further, so we are going to take the help of one numerical example. Now, let me give the statement of this particular the numerical example which we are going to solve. Now, the statement is as follows, like your say a fuzzy logic based expert system is to be developed that will work based on Takagi and Sugeno's approach to predict the output of a process. Now, the database of the FLC is shown. So, I am just going to show you the database, that is the membership function distribution of this particular the FLC, particularly for the two inputs, because for the output variable there is no such membership function distribution. So, as there are two inputs I 1 and I 2, and each input is represented using three linguistic terms, for example, say low, medium and high for I 1 and near, far and very far for I 2. So, there is a maximum of 3 multiplied by 3, that is 9 feasible solutions. The output of the ith rule, that is denoted by this y I varies from 1 to up to 9, is expressed as follows. So, I am just going to give you that particular expression for the output of the ith rule. Now, the output of the ith rule, that is y I, is nothing but a function of two input variables, that is your f of I 1 I 2, and that is nothing but a j I 1 plus b k I 2. So, what we do is we consider, so this is a linear function of the input variable. So, output of ith rule is nothing but the linear function of the two input variables, your I 1 and I 2, where j k are 1 or 2 or 3. Now, this a 1 I, for example, if I put j equals to 1, so I will be getting a 1 I is equal to 1, then a 2 I is equal to 2 and a 3 I is equal to 3, if I 1 is found to be low, medium and high respectively. Now, similarly, this b 1 I, that is I am just going to put k equals to 1. So, b 1 I is equals to 1, b 2 I is equals to 2 and b 3 I is equal to 3, if I 2 is seen to be near, far and very far respectively. Now, we will have to calculate the output of the FLC corresponding to the inputs like I 1 equals to 6.0 and I 2 equals to your like 2.2. So, this is the statement. So, this is a very simple system having two inputs and one output. So, I have got this particular I 1 and I 2 and I will have to find out this particular your output, and this is Takagi and Sugeno's based fuzzy logic controller. And let us see how to determine the output for a set of inputs. Now, if you see the membership function distribution for the inputs, like this is the membership function distribution for the first input, that is your I 1. The range for I 1 is 5.0 to 15.0, and this particular range is expressed using 3 linguistic terms like your low, medium and high. And as I told previously that for simplicity we have considered the triangular membership function distribution. Now, here, so we consider one isosceles triangle. Similarly, for this low we consider some sort of the right angle triangle, and for high also we are going to consider some sort of say right angle triangle. Now, similarly for this I 2, the second input variable. So, what we do is the whole range starting from 1.0 to 3.0, that is divided into 3 linguistic terms. That means, 3 linguistic terms are used to represent I 2. One is your this NR is the near, FR stands for far, and VFR is your very far. So, using actually the 3 linguistic terms, we can represent the input variables like your I 1 and I 2. And once you have got this particular the representation for the inputs, that is nothing but the database. So, now we are in a position to find out what should be the output for the set of inputs. Now, let us try to concentrate. So, here I 1 is 6.0 and this should be in fact your I 2. So, here there is a small mistake. So, this should be I 2. So, I 2 is equals to 2.2. Now, corresponding to your the 6.0 and 2.2. So, let us try to find out like the membership function value. So, 6.0, that means I am here. So, 6.0 I could be here. Now, 6.0 can be called medium with some membership function value, and it can also be called low with another membership function value. So, it is called medium with this much of membership function value, say mu medium, and this can be called low with another membership function value, and this is nothing but is your mu low. Now, similarly like 2.2. So, this value of I 2 is 2.2, and corresponding to this particular 2.2. So, I can find out what should be the membership function value. So, if it is very far, so this is nothing but the membership function value for very far, and similarly this is the membership function value for your the far. And once you have calculated, so these membership function value, so we can proceed further, and how to calculate this membership function value, that I have already discussed in details. Now, here, so we have got that this I 1 that is equal to 6.0. So, it may be called either low or medium. Similarly, your I 2 that is 2.2 can be called either far or very far. Now, once you have got this particular the mu value, now let us see how to determine the mu value, how to determine the mu value, and that I am going to discuss once again. Now, so here if you see, so this is the membership function distribution for low. So, I am just going to show. So, this particular right angle triangle, and it starts from 5 to and it ends at 10, and corresponding to this particular 6. So, what I will have to do is I will have to calculate this x. Now, as we have already discussed, once again we are going to use the principle of the similar triangle. So, if I use the principle of similar triangle, so I can find out what should be the value of x. For example, say, so this particular triangle is similar to this triangle, that means this angle is equal to that particular angle, and this angle is the common angle. So, I can write down x divided by 1.0. So, x divided by 1.0 is nothing but 10 minus 6 divided by your 10 minus 5, and now if I just find out the value of x, x will come out to be equal to 0.8. So, this membership value, that is your mu low, is nothing but is your 0.8. So, this is the way actually we can determine the value of the membership. So, this input I 1 of 6.0 may be called low with membership value 0.8, and the same input I 1 that is equals to 6.0 may be called medium with your the membership value of 0.2, and that is nothing but 1 minus 0.8, and that is equals to 0.2. Similarly, the input I 2 of 2.2 may be called far with the membership function value. So, mu far is 0.8. So, this can be calculated by following the same procedure. Now, the input I 2 of 2.2 may be called very far with the membership function value 0.2. So, for each of these particular the inputs I 1 and I 2, and with respect to their linguistic terms, we are able to find out what should be the membership function values. And once we have got these particular membership function values, so we are in a position to find out what should be the weight of each of these particular the fired rule. Now, before we calculate the weight of the fired rule, let me try to identify, or let me try to mention here the set of the fired inputs. Now, the set of fired inputs are as follows. So, if I 1 is low and I 2 is far. So, this is actually the first set of the fired input parameters or input variables. The second set of fired input parameters are if I 1 is low and I 2 is very far. Then the third set of fired input parameters if I 1 is medium and I 2 is far, and the fourth set of your this fired inputs is if I 1 is medium and I 2 is very far. Now, corresponding to each of these particular the set of fired input parameters, we should be able to find out the weight. Now, let us see how to find out so those weight values. Now, to determine the weight values, so what we do is, so we try to find out W 1, that is nothing but the weight of the first fired rule, and this W 1 is nothing but mu low multiplied by mu far. Now, mu low is 0.8 and mu far is once again 0.8, and if you multiply, so you will be getting your 0.64. Now, similarly, corresponding to the second the fired rule, so what you can do is we can find out the weight, that is W 2 is nothing but mu low multiplied by mu very far, that is 0.8 multiplied by 0.4, and that is nothing but 0.16. Now, similarly, corresponding to the third rule, so we can find out that is nothing but mu m multiplied by mu far, and that is equals to 0.2 multiplied by 0.8. So, we will be getting 0.16, and corresponding to the fourth rule. So, the weight will be calculated as follows, like your mu m multiplied by mu very far, that is 0.2 multiplied by 0.2, and here we will be getting 0.04. So, this is the way actually we will have to calculate the weights of the different fired rules, and once we have got this particular the weights, now we are in a position to find out in fact the output of each of the fired rule, and then I will combine. Now, the output of the first fired rule, that is denoted by your y 1, that is nothing but your I 1 plus 2 I 2. Now, how to find out this particular coefficient? The values of the coefficients I have already defined, that this I 1 is represented using 3 linguistic term, and for each of the linguistic term there is a separate value for the coefficient. For example, if it is low, medium and high, if it is low, the coefficient is 1. So, if it is medium, the coefficient is 2, and if it is the high, the coefficient of this thing is 3, and something like this. The same is also true for I 2, the coefficient of I 2. So, this y 1 is nothing but I 1 plus 2 I 2, and I 1 is what? I 1 is your 6.0 and I 2 is your 2.2. So, if I just calculate, so I will be getting the output of the first rule is your 10.4. Now, similarly we can find out what should be output for the second fired rule, and that is nothing but I 1 plus 3 I 2, and that is nothing but 6.0 plus 3 multiplied by 2.2, and this is your 12.6. Similarly, your y 3 is nothing but 2 I 1 plus 2 I 2, and that is nothing but 2 multiplied by 6.0 plus 2 multiplied by 2.2, and I will be getting 16.4. Then comes your y 4 is nothing but 2 I 1 plus 3 I 2, that means your 2 multiplied by 6.0 and 3 multiplied by 2.2, and if you just add them up, you will be getting 18.6. So, till now we have determined the weights of each of the fired rules and the outputs of each of the fired rules. Now, I am just going to find out like how to determine the output considering the combined control action. Now, this output is nothing but is your W 1 multiplied by y 1. So, this is actually the weight of the first fired rule, and this is your the output of the first fired rule, plus W 2 multiplied by y 2 plus W 3 multiplied by y 3 plus W 4 multiplied by y 4 divided by W 1 plus W 2 plus W 3 plus W 4. And if you just substitute all the numerical values here, for example, in place of W 1, I am just going to put 0.64 and y 1 is 10.4, then W 2 is 0.16 and y 2 is 12.6, then W 3 is 0.16 and y 3 is 16.4, then comes W 4 is 0.04 and your y 4 is 18.6 divided by the sum of all W values, then I will be able to find out what should be the output, that is nothing but your 12.04. So, using this particular the rule, using this particular the technique, that is Takagi and Sugeno's approach. So, we are able to find out what should be the control action or the output for a set of inputs. Now, as I told that if I want to find out the output, the first thing we will have to know is we have to know the coefficients, and as I have already mentioned, to determine the coefficient we take the help of some optimization tools, and that is why. So, this particular approach is able to provide very accurate prediction. Now, here like if we just plot, now we have already discussed like if we just plot say interpretability versus accuracy. So, supposing that here I am writing interpretability, and here I am writing the accuracy. Now, till now actually we have discussed two very popular approaches of fuzzy reasoning tool, and one is the Mamdani approach and another is actually Takagi and Sugeno's approach. Now, for the Mamdani approach, the interpretability will be high, but the accuracy is low. So, might be I am here. So, this could be your the Mamdani approach. So, this is the Mamdani approach, and the Takagi and Sugeno's approach, the accuracy is actually high, but interpretability is not good. So, might be that particular point is here. So, this is nothing but Takagi and Sugeno's approach. So, this is actually the real situation of these two algorithms, but what we want is we want one algorithm which will be able to do the prediction accurately, and at the same time its interpretability should be good, and that is why we try to find out one algorithm, and that algorithm may take the position somewhat here, and that is it will give some sort of the better prediction, but not at the cost of computational complexity. So, it should be computationally tractable, it should be interpretable, and at the same time the accuracy should be good. So, might be we are going to search for the algorithm which could be here, and that will provide a very good combination of this particular accuracy and interpretability. That means, my expected fuzzy reasoning tool should be such, in fact, like if I just read the rule, some control action should be understandable, and we should be able to understand the output of a particular the rule, and at the same time the accuracy should be good. And a lot of studies have been made how to find out an algorithm for this the fuzzy reasoning tool, which will provide both accuracy as well as interpretability. Thank you.